Module 5 of Principles of Database Design. The first half of this module mainly deals with indexing mechanisms. So, the main objectives of this particular video session would be to understand what we mean by indexing in database, what is the need for indexing, how it is performed, and what would be the advantages of having such a mechanism. So before moving to indexing in database, let's try to understand what indexing means in general. Imagine you need to search for the particular topic in your textbook. The easiest way to do it would be go to the backside of the text in the index portion. The topics would be listed in alphabetic order. Search for the topic, look the corresponding page number, go to that particular page and reach that particular topic. So similar to this feature, we can have a similar feature in database also. So the whole use of indexing is to speed up the retrieval of records or information or searches. So let's see how such indexing mechanisms are performed in a database. There are two types of indexing actually. We'll be dealing in depth with all this. There are single level index and multi-level index, and within single level index there's primary, secondary and clustered index. In this particular video we'll be dealing with just the primary index. Now before moving to how indexing is implemented, let's see how in general a query is executed, what happens when a query is executed, all those things. Now imagine we have a query. We have been dealing with how to write queries in the past few modules. So we have a query like select star from employee where name is Wong. So this particular query would retrieve a single row, that is a row corresponding to name equal to Wong from the table employee. So now imagine this is your database. Before moving to the example, we need to understand one more thing. You might have studied that now this database is stored in secondary memory. Now, and the data is stored as blocks. And whenever something a query is to be executed or a program is to be executed, things have to be brought from the secondary memory to the primary memory. Now this transfer from secondary to primary happens as blocks. So data is stored as a block in memory. There can be number of rows in a single block. So and there can be number of blocks to store a particular table. Now if we need to execute this particular query, that is select star from employee where name is Wong, so we don't know where this Wong is. So what we'll do is, if we are going for the linear search, which we have already studied in data structures, we will look whether this first row is Wong, second, third, fourth, and until we reach Wong. And if we are doing so, the average complexity would be n by 2, where n is the total number of records. Now imagine if there were 3000 records, we would have to search 1500 records on an average to reach our desired result. Now since you might have observed that the entries in this database are sorted or are ordered alphabetically. So we have a provision of performing binary search, and the complexity of binary search, you might have studied that it's log to the base 2 n. So we need to perform at least log to the base 2 n block search to reach the particular block where that particular name lies. So if this is the query, we need to actually fetch this particular block. We are not actually fetching this single row alone. We need to actually fetch this whole block to primary memory. So that is our aim. So without indexing, we have to perform log to the base 2 n over all these blocks. Now let's see how indexing can speed up the retrieval. The whole use of indexing is to speed up the retrieval. Let's see how we can implement an indexing mechanism. The particular mechanism we'll be discussing in this particular slide or figure is primary indexing. So let's see how primary indexing is implemented. Imagine this is your database table employee, It consists of fields like name, SSN, birth date, job, salary, and so on. And this many records are stored as a block. This is the next block, and so on, so on. And corresponding to each block, there is an index entry. There's another specialty to this index entry. The first record in each block, that is, in this it is Aaron, in this it is Adams, in this it is Alexander, forms the index entry. You can see that Aaron is the index entry over here. As I forgot to mention that this is the index file. So index file consists of index entries. So Aaron is the index entry, and we have a pointer to the block where Aaron is stored. Then Adam is the second index entry, and we have a pointer to the block where Adam is stored. So we have an index entry corresponding to each block. And to be specific, we have the index entries are actually the first record in each block. And we have a name for that. It is termed as block anchor. That is, Aaron is the block anchor for this block, Adam is the block anchor for this block, Alexander for this block, and so on. And this block anchors that, and it is the primary key in this. And for this example, we have assumed that the names are unique and they can be considered as the primary key. You could have, and we are actually building the index on this particular field, that is name field, which we have considered to be the primary key. It's an example from your textbook. The SSN could also be your primary key, and you could have created an index on SSN also. In this example, for the time being, we are creating the index on this name field, and we are considering that name is unique. So all the names in this database are unique, and we have considered that to be the primary key field, and we are creating an index on this primary key field. So let's see how the index is created. We have there will be a block anchor and a block pointer pointing to the particular block where the block anchor lies. And the index file is denoted like ki, pi. For example, k1 p1 would be, k1 is Aaron, p1 would be the pointer to the block where Aaron lies, k2 would be Adam, and p2 would be the corresponding pointer. So if when such a query comes, select star from employee where name is Wong, instead of performing a binary search on over all these records, we can now perform a binary search over this index file. We'll shortly see what is the advantage of performing a binary search on this index file over performing a binary search over the whole set of records. So if we are performing a binary search on this index file, we have few index entries. Can you say why? And can you also say how many index entries would be there corresponding to this many records? The number of index entries would be equal to the number of blocks, because we have one index entry corresponding to each block. So how many blocks are there? Only that many index entries would be there. So the number of entries over here is reduced. Also, the size of the entry is also reduced. We'll be seeing it numerically how that speeds up the whole process. So instead of performing a binary search over here, now we need to perform a binary search over the index file, and that should actually speed up the process. We'll be looking into that using an example. Before moving into that, let's be thorough with the terms. The indexing field is this particular field on which the index is built upon, or the block anchor is included. Then we need to understand now, instead of performing a binary search over all the records, now we need to perform a binary search on the index field. And you need to also keep in mind the number of index entries in primary indexing would be equal to the number of blocks, because we have one index entry corresponding to each block. So with that notion, we can try to solve a numerical problem to understand how indexing can speed up the retrieval process. For that, let's take an example. Let's imagine there are a total of 30,000 records in our database. That is if this is the database, it consists of 30,000 rows, and we have considered the block size to be 1024. So that is, this particular block is of size 1024, and we consider each record length to be of 100 bytes. That is, each row is of 100 bytes. Now you can easily calculate how many records can be stored in each block, and that particular term is BFR, that is a blocking factor, that is how many records can be stored per block, that is known as the blocking factor. So if the size of the block is 1024 and 100 is the record size, 1024 by 100, you can actually store 10 records per block. 10 records can be stored per block. I hope you're aware of the ceiling function and the flow function. This is the ceiling function, which means that 1024 by 100, it comes to 10.24, and we will be taking 10 because 10 whole records can be stored in the block, and we cannot store half of the record in a block and half of the record in another block. So to take 10, the whole number as 10, we apply the flow function. So if 1024 is the block size and 100 is the record size, we can store 10 records per block. Again, understand, a record is this particular row which is of 100 bytes. A block is this whole thing which is of 1024 bytes. So we can store 10 records per block. So how many such blocks would you require to store the whole 30,000 records? Obviously, it is 30,000 by 10. Because why 10? It is because 10 records can be stored per block. So 30,000 by 10, 3,000 blocks are required to store 30,000 records. I repeat, 30,000 records are there in total. 10 records can be stored per block. So we require 30,000 by 10, 3,000 blocks to store the whole 30,000 records. Now, we are actually performing a binary search over this 3,000 blocks to reach a particular record. So performing a binary search over this 3,000 records means it would come to an average complexity of log to the base 2 3,000, which is 12 block access, which means we would have to at least search 12 blocks to reach the block where our particular record lies. Let's try to analyze how a particular retrieval would happen with indexing. Okay, that we can analyze after the next slide maybe. So if there was no indexing, consider this portion alone, we would have to perform at least 12 block access. If it is 30,000 records with a block size 1024 and 100 bytes per record, we would have to perform at least 12 block access to reach the correct block. Now let's see how we can speed up this using the indexing mechanism. Now for that, let's take the example. This whole row is of size 100 bytes. This field alone, let's consider it to be of 9 bytes. That is, your anchor record is of 9 bytes. So each index entry, and at the pointer size, let's assume it to be 6 bytes. So 6 bytes, that's written over here. V, which is the ordering key field, is of 9 bytes. Block pointer is of 6 bytes. So each index entry would be of 9 plus 6, 15 bytes, right? So each index entry would be of 15 bytes. Now can you calculate how, now the block size is constant 1024 itself, how many such index entries can be stored in a single block? It is 1024 by 15, because one index entry takes 15 bytes. So 1024 by 15, 68 index entries can be stored per block, so that the blocking factor for the index is 68. where over here it was 10. Okay, so 68 index entries can be stored in each block. Now let's see how many such say total number of index entries, how many index entries are there in total. We we, we had seen that the number of index entries would be equal to the number of blocks, and the number of blocks in this example is 3000. So there will be a total of 3000 index entries over here. So, and to store this 3000 index entries, let's see how many blocks are required. So we can store 68 entries in a single block. So, and there should be 3000 entries because there are 3000 blocks. So 3000 entries requires, and a single block can store 68. So 3000 by 68, we require 45 blocks to store this 3000 index entries. So the whole index entries can be stored in 45 blocks. Now don't get this figure wrong. This is not a block, whole block. There will be 68 entries as one block. There will be another 68 entries as another block, and so on. So there will be a total of 45 such blocks to store the index entries. Now what is the advantage of that? So now we need to perform a binary search over this 45 blocks, which comes to log to the base 2 45, which is 6 block access. That is, for the index entries, if we search 6 blocks, we can reach our desired name. Whereas over here, it was 12 block access. That is, without index entry, it was 12 block access. Now we can reach the desired record using 6 block access. It is not 6 actually, it is 6 plus 1, because I will just explain. Look at this figure. We are performing a binary search on this index file. So over this index file, within 6 block access, we can reach the correct block. Once we reach a particular block, to reach from that particular block to this block, because there's a pointer pointing to the block where it lies, that would require one more block access. So 6 block access over here plus 1 to reach over here, it makes 6 plus 1 7 block access. Still it is worthy because without indexing we had to do 12 block access. Now we just require 7 block access. And if you still have a doubt how a search is performed using indexing, let's take the example of searching for, say, angel. We are searching for angel using indexing. Now using binary search, we'll be knowing that angel is going to lie between this Anderson and Arnold. So we know that angel lies after Anderson but before Arnold. So we'll be searching the block that Anderson points to, that is this particular block, and this block would be fetched to the primary memory if it is angel that we are searching for, the row corresponding to angel we are searching for. That is how the search is performed. So let's just quickly revise this example. There were a total of 30,000 records. A single block has size 1024. A single record is of size 100 bytes. We can store 1024 by 100, that is 10 records per block. And how many such blocks we require? There are a total of 30,000 records, 10 records per block, so 3000 blocks are required. And to perform a binary search on 3000 blocks, we require 12 block access. Now if you are going for indexing, each index entry is 15 bytes, that is 9 plus 6, 15 bytes. So block size is 1024. We can have 68 index entries, and there are total of 3000 blocks, so there should be 3000 index entries, and 3000 index entries can be stored in 45 blocks because 68 index entries can be stored in a single block. and performing a binary search on 45 blocks would require 6 block access, and that is over the indexing. There is 6 block access over here and plus 1 to reach this particular block, so that is 6 plus 1 7 in place of 12. So that is the advantage we are having by going for indexing. Now, how is this advantage obtained by indexing? We saw that the index entry are fewer in number. If there are 30,000 records over here, or 3,000 blocks over here, there are only 3,000 index entries for 30,000 records. So they are few in number, and also each index entry is of less size. So more index entries can be accommodated in a single block. So performing a binary search over the index entry uh, is much more faster when compared to performing a binary search over all the records. So that are the advantage primary index has. You can read all this in the notes that has been provided to you. Then one drawback we can discuss for this primary index is sorry, what happens when we insert or delete a particular record. Now imagine you need to insert a record, and if things are stored in an alphabetic manner, if you need to insert a record in this place, this particular record needs to be pushed one place down, right? So if you are inserting a particular record over here and this is pushed one place down, this archer would become the anchor record of this block instead of Arnold. And if that happens, you need to modify the index file also. So as you insert one entry, all the entries below that needs to be shifted one place down. So all the anchor records below that entry would be changed. So each time you make an insertion, if you need to change the anchor record or if you need to update the index file, it is going to be a difficult task. So that is one disadvantage we have. And similarly regarding deletion of the records, imagine you are deleting Arnold. If you delete Arnold, all the records below Arnold should be shifted one place above. So this, if you are deleting Arnold Mac, Arnold Steven should be the anchor record of this block, and similarly every anchor record of the blocks below would be changed. So similarly the index file should also change. So corresponding to each insertion and deletion, if we need to keep on updating the index file, that is going to be a difficult task. There are solutions to that, which you can read in the notebook. There are solutions like you can attach another block to this block if you need to insert, and the insertions can happen in that block, and similar data structure mechanisms are there which you can have a read from the notebook. So that was regarding primary indexing. This is how primary index is performed. Just to recollect, primary index, for primary index to be performed, the field on which index is created should be the primary key, or it should be unique. And the first row of each block becomes the index entry in the index file. That is how primary index is performed. So we saw how the retrieval, or the how we can reduce the number of block access by going for an indexing mechanism and without indexing mechanism. And to categorize indexing, there are two types of index actually, dense and sparse index. We'll be winding up the video with this comparison. Actually we can there are two mechanisms. Either we can have an index entry for each and every record in the file. So let's say, like, if you have 30,000 records, we can have 30,000 index entries. Or say in the primary index example which we took, for 30,000 records there were only actually 3,000 index entries. So there are fewer index entries compared to the number of records. So such indexing mechanisms are termed as sparse or non-dense index. And if we have an index entry for each and every record, it is termed as dense. So primary indexing is a kind of sparse or non-dense index mechanisms. In the further lecture videos, we'll be seeing the next type of indexing, that is clustering, secondary index mechanisms, and comparing all these terms. So what we just saw in this video lecture was just an overview, and I hope you have understood this example. When you go back and read the supplementary note which you have, try to understand this particular primary index using this particular example, that is what happens without indexing, how binary search is performed without indexing, how it is performed with indexing, and what is the advantage you obtain by going for such an indexing mechanism. So in the next lecture, we will be seeing the other indexing mechanisms. So thank you. Thank you for listening to this lecture. Thank you.